Hey y'all, we are finally finishing the last of chapter 9, which again is going to cover the reactions of alkyne groups of the triple bonds. So here it is, the last lecture of Summer Organic 1. So some reactions of alkynes that we will be going into kind of fall into two general categories, and we'll be talking about all of these. One is reactions of the terminal alkynes. So that is, again, an alkyne that is at the end of a hydrocarbon chain. So it will look like this. It's at the end of a chain. So these terminal alkynes have a little bit of special chemistry, and in particular via the acetylide anions. Now, acetylide is just a carbon-carbon triple bond that has lost one of its hydrogens, making it an ion. So it looks like this. This is the acetylide anion. So it's the simplest form of an alkyne. And we can do a lot of chemistry specifically with this very simple alkyne. The particular type of reactions we'll be talking about as far as terminal alkynes or those acetylide anions are alkylation. That's the addition of an alkyl group. Remember, alkyl means a carbon-carbon bond. And other SN2, so substitution-like processes. Then we're going to be talking about general additions that can occur over a triple bond. We talked about addition reactions on double bonds at length, and triple bonds have very similar types of reactions. They also undergo addition reactions, very similar to double bonds. So a lot of this will be similar to what you learned in the last chapter in double bonds. We're going to be talking about hydrogenation, so using hydrogen to reduce a triple bond. Electrophilic addition of an HX, we saw that on a double bond. Electrophilic halogenation, that's where you have a halogen gas, X2, and how you add that across a triple bond. And then ozonolysis, which we also talked about in double bonds, and we'll see how these act on a triple bond. Okay, so first let's talk about preparation of alkynes for alkylation. The idea of an alkylation reaction is that you can replace a hydrogen with an alkyl group. That's, remember, any carbon group like a methyl group, an ethyl group, etc. So you can place it, substitute it out essentially for a hydrogen. Now, terminal alkynes can be alkylated by first turning them into an anion. So the key thing here is that that triple bond has to have one of these hydrogens on it. Remember that terminal alkynes have these free acidic hydrogens. This is key to do an alkylation on a triple bond. They can't be an internal triple bond. So these terminal alkynes, they can be alkylated, so we can put on a new group first by making them an ion. So there's a prior step of making them an acetylide anion to then add on the alkyl group. So the first step is to use a strong base. We actually talked about this in the last section. If we use a strong base such as an amide ion, right? This is NH2 minus, it's attached to a sodium. This is an ionic bond, so this is a plus and this is a minus. We're going to use this strong base to remove one of these protons. And we make an acetylide. That is a triple bond that now has its proton, one proton removed, and it has a negative charge. So the key thing here is essentially you're generating this. We used to have a proton here. We removed the proton. This can be connected to whatever, and it now has a negative charge. Okay, so it is an ion. Notice here it's connected to sodium. Sodium, again, this is an ionic bond. It's just being a placeholder. But the key thing is we make this anion, this negatively charged triple bond. And that's why it has to be a terminal or this acetylene, which is just a triple bond that has a hydrogen on each side. Only these will work. Once you make that acetylide, that anion, then you can substitute on a carbon group. Now, the acetylide is very strongly nucleophilic. It's going to act as the nucleophile in this reaction. And it's going to act through an SN2 substitution, but it is the nucleophile, and it is going to react with a carbon group. So we actually add a carbon group on. You thus end up with this alkene. It's still a triple bond, but now we've just extended it. We've added on carbons. Again, these acetylide ions are strong bases once we make them, and they are good nucleophiles. So they can act in an SN2 reaction as a nucleophile. So here you can see this is a terminal triple bond that has been made into an acetylide ion, right? It has its negative charge. So we did our first reaction with the strong base to remove the proton. We made our acetylide ion. Then we can add this group. This is showing R can represent any carbon group, any length carbon group attached to a CH2, which is attached to a bromine. So you'll see some halide there. And we're going to form a carbon-carbon bond and break this carbon halide bond via a substitution. Now, an acetylene, that's the molecule that is the simplest triple bond. That's this molecule. Acetylene can have this happen to it twice because it has two of these terminal protons, and any other terminal triple bond, which is attached to carbons, can have an alkyl group added to it one time on one side. Now, the scope of the electrophile in the SN2 reaction still applies. That means that in this case, remember, our triple bond is the nucleophile. So our electrophile is this group. And for an SN2 reaction, the electrophile must be a methyl or primary alkyl to have a good reaction. So it works best when these groups that are being added on are a methyl group or a primary halide. So usually we'll have the halide at the very end of the chain here, and then whatever we want to add on here. So for example, this reaction would not work well if we had something like this, a tert butyl on a bromine, and we were trying to add that onto the triple bond. And again, this is because we're still technically doing an SN2 reaction, and SN2's biggest barrier is that steric hindrance. So the reason this is special, the reason we're talking about this a lot is because notice the type of bond that is formed. We're forming a carbon-carbon bond. And so far, we have actually not shown any examples of making a carbon-carbon bond, so extending a carbon chain. These reactions are very important because we can extend a carbon chains. They help us synthetically. There are other reactions that you will get to later in Orgo 2, but they're very limited as far as the types of reactions that do this carbon-carbon bond formation. So this is one of a few reactions that let you extend the carbon chain. So again, as a whole, this idea is that we first have to deprotonate our triple bond to then further add onto it. Here again, we're showing that if you start with this acetylene, this is a triple bond that has initially had a proton on each side. You can extend it on both sides of the triple bond. So first we remove this proton, it's already gone. It's the acetylide ion is already made. And we're adding a 2 carbon long chain. So here's that 2 carbon long chain. And then we can remove this proton. So we put some more strong base there. And we can then further extend in the other direction. This is a 3 carbon long chain. So you can see here is the 3 carbon long chain. So we can make things that are unsymmetric alkynes. We can add on all kinds of different carbon chains onto a triple bond. So they are a great way to form molecules via carbon-carbon bonds. So thinking about what we just talked about, what alkyl halide would react faster with an acetylide ion? So you've made an acetylide ion in this SN2 reaction. So we want to do an SN2 reaction. We want to extend the acetylide ion by adding on some carbons. Which of the alkyl halides would be better? So remember, this is an SN2 reaction, and as I just said, it is limited, the alkyl halides are limited to being usually primary or a methyl group, methyl halide, so that they are not sterically hindered during the SN2 reaction. So we look quickly at these. These are all alkyl halide groups. You can see this is one where the bromine is on one position. That would be this, 1, 2, 3, bromopropane. Here's 2 bromopropane, tert butyl iodide, that's this group. And 1 bromo, 2 methyl butane. Okay, so oh, put my methyl in the wrong place, right here. So even though, for example, this group and this group both have the bromine on a primary carbon, you can see that group A is going to be the one that has the least steric hindrance. And remember, that's important. You want these primary chains for this type of reaction, for an SN2 reaction with the least amount of steric hindrance. And so A would be the answer. Okay, so now let's talk about how we can prepare alkynes. We talked about using alkynes for an extension and adding carbon-carbon bonds on them, but let's talk about how do we make alkynes. Alkynes can be formed via elimination, just like we can form double bonds via elimination. The most simple form of this is transforming a double bond into a triple bond through dehydrogenation. We saw how you can do this with a single bond, right? So you could take a single bond and remove the hydrogens, dehydrogenate to make a double bond, and we can further remove hydrogens to make this into a triple bond. So this is the simplest version of an elimination reaction to form a triple bond. Dehydrogenation, just like normal dehydrogenation to form a double bond, is expensive because it also requires a catalyst to do this type of reaction. Another form of elimination you can do to form a triple bond is through the elimination of a dihalide, two different eliminations of a HX group. So two different types of halide molecules can be used to make triple bonds. The terms for these are geminal or bisinol. A geminal dihalide is when the carbon group has the halides both attached to it. So one carbon of the carbons that will then make the triple bond has both halides on it. Or you can have them as bisinol, where they are in a 1-2 position. So they're along the two carbons that will eventually make the triple bond. Both of these will result in a triple bond when reacted with a strong base. As we've seen before, this amide ion, which is used for removing protons strongly to form an alkyne. Now, these methods are typically used to make terminal alkynes, because when you do them internally, these double eliminations, we're doing two eliminations because we have to eliminate to make a double bond and then eliminate again to make a triple bond, usually have regioselectivity issues, but you can still accomplish making an internal triple bond. When you make an elimination reaction using a geminal dihalide, both of these halogens, again, are bound to the carbon. In this case, normally the terminal carbon of a final terminal triple bond, and are then reacted with 3 equivalents of base. This is key. You actually need 3 per one molecule, one starting molecule, to make your final product. Now, what's happening here is that there are 3 reactions that are happening with the base. The base is going to remove 1 chlorine, a second base will remove a second chlorine, and you've actually at this point already made your triple bond, but a third reaction will occur in which you remove the proton from the triple bond, making what we just saw, which is an acetylide ion. If you use all three, you'll make this, and then water is usually added to reprotonate that triple bond to make your final product. So you are required 3 equivalents. There is rapid and irreversible deprotonation, which then has to be followed with addition of water to make your final alkyl group. So similarly, if you were to make a terminal triple bond using a vicinal dihalide, you would have one halide on the end group that you want to be the terminal triple bond, another on the carbon that is adjacent to it. Again, you need 3 equivalents of base. You will generate an acetylide ion, which then again has to be worked up with water. Water needs to be added to then form your final alkyne. So this type of formation of brominating to then make a triple bond, as far as starting with a double bond, brominating in the 1,2 position, and then doing this elimination reaction for a triple bond is a good route if you can't do dehydrogenation. So this elimination through our removal of halides, dihalide removal, is good if you don't have a dehydrogenation process and you can't use catalysts. It's very expensive to use catalysts just to remove the hydrogen. So although our dehydrogenation process is probably the most straightforward idea, heat and catalyst to remove the hydrogens from a double bond to just make a triple bond. Another way to go from a double bond to a triple bond is by using this elimination reaction of dihalides. Okay, to reiterate what we just went over, how many equivalents of sodium amide, our strong base, are needed to carry out the double dehydrohalogenation of 1,2-dibromopentane? Let's draw what this looks like. So here's a pentane. There's a bromine on 1 and 2. Okay, now we want to do a double dehydrohalogenation. That means that we're going from this single bond to make a triple bond. So here's our final product that we want. This has 1, 2, 3, 4, 5 carbons. And to do this reaction, we are going to need Na, NH2, and we will need 3 equivalents of it, remember, and then water. So 3 equivalents are needed to do this reaction. Now, which of the following compounds yield 1 heptyne, that's a triple bond, on being treated with 3 moles of sodium amide, and then followed by adding water to the reaction mixture? So this is the type of reaction we just looked at, sodium amide with water. We know that if you use 3 moles, you will generate a triple bond. Now, to do this, remember you have to have two halides and they have to either be geminal or vicinal to make the desired product. The desired product here is heptyne. So it's a 7-membered chain, and it has, I should draw this like this. So that's a 7-member chain with a triple bond, and so this is what we want to make. And we need to start with something that has either geminal or vicinal halides on a 7-membered hydrocarbon chain that we then can react to form our wanted product. So in this case, the first example A has a 1,1,2,2 tetrachloroheptane. It's a heptane, so it's a 7-member chain. And it has chlorines. It has a lot of chlorines on it. It has chlorine here, 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 and here. Will this work? No, it will not. There's very strict rules about this being geminal or vicinal. They have to be only 2 halides, either both attached to one carbon on the terminal end or adjacent to each other. So this is actually too many halides for this reaction to take place. Those hydrogens are also needed when removing the halides. Okay. Our next one, B, is a heptane as well. And it has a bromine on position 1 and a chlorine on position 2. This checks the box for it being vicinal, so they are adjacent to each other, but they are 2 different halides. Is that okay? The answer is yes, it is okay. It's fine to have 2 different halides for this reaction. Each of the parts of the removal take place one by one, and it's okay for them to be separate but similar reaction rate halides. So these are fine. B would actually work just fine. What about C? C is a pentane actually, so it's not even long enough. It's this, and it has a chlorine here, here, and here. So again, too many halides, and it's not even a long enough chain. So our answer here would be B. Okay, let's talk about hydrogenation of alkynes. We touched on it. It is the easier reaction, dehydrogenation is the easier reaction when trying to make triple bonds. Dehydrogenation, that's going from a double bond to a triple bond. But here we're talking about hydrogenation, the opposite, which is adding hydrogen to a triple bond to go back to a single bond. Hydrogenation can occur, again, just like we talked about with double bonds. You can hydrogenate a double bond using hydrogen and a catalyst, platinum, palladium, nickel, rhodium. It acts the exact same way as we saw with an alkene. In this case, you just need 2 equivalents of hydrogen over a metal catalyst to make your alkane. Hydrogens also add in a syn manner, just like what we saw with a double bond. So the hydrogens always add to the same side of the molecule. The second hydrogenation reaction, again, is just a reaction of an alkene. We've already seen this. So we'd go from an alkyne, we add hydrogens on. here and here on the same side, and then 2 more hydrogens would get added on to the same side of this molecule to make our final alkene. However, when you do a hydrogenation of an alkyne, this process will not stop. It will just go all the way until it forms an alkane. You'll go from a triple bond straight to a single bond using this metal catalyst. So what if we want it to stop at a double bond? What if we want that double bond and not the single bond? How do we stop it at the alkene stage? Well, you do a special kind of hydrogenation called a Lindlar hydrogenation. This is using what's called a poisoned catalyst. It's a slowed catalyst, so it doesn't act as fast, and it allows for selective hydrogenation. It specifically will make a cis-type alkene, if it's possible, if the cis is possible. You might not have any stereochemistry on the resulting double bond based on the position of that starting triple bond. But if you do have the availability of stereochemistry, this will make a cis alkene. And remember, that's because the hydrogens add in a syn manner. They add on the same side, and so you'll make a cis bond. So for example, if you start with this molecule here with a triple bond on it and you used a Lindlar catalyst, this is the actual setup of the Lindlar catalyst. Usually you will see it just written like this, Lindlar palladium. It's a Lindlar poisoned catalyst. That's how you'll see it written. So if we were to use a Lindlar catalyst, we will hydrogenate only to the double bond. So the product is the same, except now our triple bond has gone to a double bond. Here's a decyne. This is a triple bond in a 10-membered chain. Notice that the final product is the cis formation of the double bond. This is when you have same side cis formation of the double bond. So let's do a practice problem. What is the product that is isolated from the treatment of 2-hexyne with the Lindlar palladium catalyst? So 2-hexyne, let's draw that. Hexyne, that's a 6-membered chain with a triple bond on the second carbon. Now we're going to do a Lindlar reaction in which this will become a double bond, and pen is just not working with me. Let's redraw this. Draw it correctly. 1, 2, 3, 4, 5, 6. This should be 4. Draw my actual planar carbon. So 1, 2, 3, 4, 5, 6. Okay, this triple bond here will become a double bond, and when we add our hydrogens, they add to the same side, making these bonds a cis formation. So they should be in this same side cis formation when you form that double bond. So this is a 1, 2, 3, 4, 5, 6, still a 6-membered chain with now a double bond because we did a Lindlar hydrogenation, and it should be in the cis formation. So that would be answer B. Notice that this is the cis formation of the double bond, whereas this is the trans formation. Trans is the opposite side, cis, same side. Remember that we could also write this as Z and E. Okay, now let's think about these reactions we've talked about on a bigger scale, combining them together. We're going to be talking more about combination of reactions and retrosynthesis as we did previously, and you're going to dive more and more into retrosynthesis into Orgo 2. Let's think simply about how we would go from something like a triple bond to a longer double bond. Here we want to synthesize cis to pentene. This is a double bond and it has a cis formation. So this is, we know that there's going to be double bond that is cis, like this. It is on carbon number 2. 1, 2, 3, 4, 5. So it's 5-membered chain. Here's our final product we want. And we're starting with a prop-ine. That's only a 3-membered carbon with a triple bond. So here's carbon 1, 2, 3. So we need to go from something with 3 carbons to something with 5 carbons, and we also need to go from a triple bond to a cis double bond. We talked about both of the reactions that you can do this with. There are 2 different reactions we talked about. One was our acetylation, or alkylation using an acetylide ion. That was the very first reaction we talked about, and that helps you extend your carbon chain, right? That lets you add on carbons to a terminal triple bond, which we have. This is what we're starting with, terminal triple bond. So we can add carbons on. And we also talked about how to go from a triple bond to a cis double bond. That's using the Lindlar catalyst. So let's look at our available options here. Notice they're all pretty similar. We start with a strong base that it will deprotonate our starting reactant, our terminal triple bond, making it an acetylide ion. Then we're going to add on, using a substitution reaction, some chain of carbons. And we have to think about which of these would be best. We're starting with something that's a 3-membered chain, and we're ending with a 5-membered chain. So we need to add 2 more carbons on. So notice that only one of these then is canceled. B is only adding 1 carbon on, so can't be B, but the rest of these work. 2 carbons, 2 carbons, 2 carbons. It doesn't necessarily matter what halide you have attached to it, bromine or iodine. We're adding some alkyl halide that extends our carbon chain by 2. Now, lastly, we want to use a Lindlar catalyst to make a double bond that is cis. So the only one of these that does all 3 of those is answer C. It uses 2 carbons here and then follows up by a Lindlar catalysis to make a cis double bond. So combining these 2, especially using the first reaction we talked about, this NaNH2 followed by some extension, is going to be very key in doing these reactions with triple bonds. And you can do multiple reactions with them. Okay, now let's talk about addition reactions on a triple bond using hydrogen halides. These are going to, again, be very similar to what we saw with double bonds. You can add HX, any hydrogen halide, across a alkyne to form an alkyl halide. So you now have a double bond with a halide on it. These follow Markovnikov's rule, just like with a double bond addition. They're very similar. They're essentially the same, except we're going from a triple bond and we're resulting with a double bond that has a halide in it. These are a concerted reaction, and so their rate constant is as shown. You actually use 2 halide molecules per one reaction to add on the X, the halide, and the proton to either side of that triple bond, opening it up. You can stop the reaction at the double bond, so you can stop it by just adding 1 HX, you'll make this double bond. Or you can add a second HX to your now double bond. So now we're doing a addition reaction on a double bond, still following Markovnikov's rules. If you do a double reaction because you want to add to the more substituted carbon, you would add your halide on each end of that carbon, forming a geminal dihalide. So which of these products, when isolated, would be isolated when you do the reaction of an addition of 1 equivalent of HBr to hexyne? So we're starting with a triple bond. It's 6 long, and the triple bond is on the 1 position. So 1, 2, 3, 4, 5, 6 membered chain, triple bond on the 1 position, and we're adding 1 equivalent of HBr. So only 1 equivalent of HBr would add across that triple bond, leaving a double bond. So we have a double bond here. And the bromine is going to follow the Markovnikov rules, meaning it will add to the side that is more substituted, and the hydrogen will add to the side with more hydrogens. So the bromine will add here on the 2 position. So your answer here should be C. We retain the double bond and the bromine adds onto the 2 position following Markovnikov rules. Now, what if you add excess halide, hydrogen halide? So let's add excess HCl to a 1-butyne. Similar, this is a triple bond in the 1 position. So this is a butyne 1, 2, 3, 4. We're going to add HCl in excess. So that means it can double react. When you double react, this becomes a single bond. So this is now a single bond. Our first chlorine adds to the more substituted position, which is here. And then our second chlorine also adds to the more substituted position, which is here. So you would get 2,2-dichlorobutane as the resulting product. Now, what about hydration of alkynes? We also talked about hydration on our alkenes, on double bonds. And when you hydrate a double bond, you form an alcohol. Now, technically, when you do that to a triple bond, you do the same thing. The product is a special type of alkene, because again, it retains that double bond. and it now forms an OH on it. This is a special type of double bond carbon called an enol. So similar to what you would see when you open up a double bond with water. So if this was your double bond and you open this double bond up with water, right, you would have an OH group and form an alcohol. When you start with a triple bond, you reduce to a double bond and add an OH group. And this double bond with an OH group is called an enol. These are not isolated. We've actually seen enols very, very briefly at the very beginning of this course when we were talking about resonance. Enols have a resonance form that they very quickly will convert into. That is a ketone. And we talked about ketones in our functional group. We introduced them briefly when we talked about functional groups. So ketones are a type of functional group. So enols will be formed and then they very quickly undergo this isomerization, this fast transfer into a ketone. This type of isomerization, this type of reaction between an enol and a ketone is called a tautomerization. You see this all the time in biology. Biochemical molecules undergo tautomerization very frequently, specifically between this keto and enol form. Again, the ketone form, the keto form, is the more stable and the form that you will see as the main product that you will isolate just floating around. This is the same for biological forms and biological molecules. The keto form is the most stable and what you will see. However, the enol form is very important because sometimes the enol form is what's used in a reaction, especially in enzymes. So again, biologically, this tautomerization concept is very key. So again, alkynes will form this enol that then becomes a ketone. So notice that our double bond has now essentially transferred to where this oxygen was. The tautomerization is just a migration of a proton between the oxygen and the carbon. And during this migration, you also have migration of electrons. Realistically, it's all a migration of electrons that then moves the double bond between that position on the carbon to the position on the oxygen. These have to be catalyzed usually by an acid, but can be catalyzed by a base as well. So when you do a reaction of an alkyne with water, it has to be done in a acidic, very acidic, or a very basic, usually very acidic environment. We also can use mercury as a Lewis acid catalyst along with the acid and water to help this reaction occur. So sometimes you'll see mercury written here, or again, we can just use this strong acid, and here's our mercury form HgSO4 along with it. So again, you'll have some acid, and then oftentimes you'll see mercury along with water and your triple bond to make this hydration reaction occur. So if you look here, if we start with octyne, triple bond, it would open up. You can think about it first opening up into an alcohol, and wherever that alcohol would be, instead will form the ketone. So if here's our triple bond, and we were to add our OH group on it from our hydration. This triple bond then becomes a single bond and we form the ketone there. Similarly with octine, we're going to follow Markovnikov rules when we add our alcohol on. When the oxygen is added on, it follows Markovnikov rules because this is an addition. So notice that between these two carbons, if we're going to add an alcohol onto either of those, the more substituted carbon would have the alcohol added onto it, which is here. And then that alcohol will become the ketone form. So you can see we result in a ketone on the 2 position. Let's try a practice problem. The acid catalyzed hydration of 2-hexyne gives what? So let's draw 2-hexyne. Here's our triple bond, 1, 2. Now, if I were to hydrate this triple bond, think first about adding on an alcohol. The first part of it, we're going to add some oxygen group on here, and it's going to follow Markovnikov rules. This is still a type of addition reaction. So we still want to follow where the most substituted carbon is. Now, along this triple bond, actually, each side is equal. You'll notice this side or this side are both the same as far as substitution. So you could add on either position, and then that position will become the ketone. So ultimately, we could form this compound in which the ketone is on position 2, or the ketone is on position 3. Either of these are valid because of that starting placement of the triple bond. Both of them have the same substitution level, and so either product could form. So A or B technically is the correct answer. So both A and B would form in this case. Now let's go into the addition of halogens across alkynes. We talked about these hydrogen halides like an HX, but what about when we have a hydrogen, or excuse me, when we have a halogen gas? Again, these react very similar to what we saw with a double bond. With a double bond, we add our halogens across a double bond in an anti-addition. Remember that halogens are anti when they add, whereas hydrogen is syn when it adds. So in the case of a triple bond, it's the same type of addition, except our triple bond goes to a double bond, and those bromines get added in an anti-fashion. So you result in a trans formation of the double bond. Now, if you use 2 equivalents of the halogen that you start with, you can halogenate fully. So you'll halogenate the triple bond to a double bond, and then you'll halogenate that double bond into a single bond with more halogens on it. So here, if we start with this triple bond and we halogenate fully, you'll see that you end up with 4 chlorines across where the triple bond once was, but now a single bond. Lastly, we'll talk about ozonolysis, which we also looked at in the context of a double bond. Remember that when we have ozone with water, it will split a molecule into carbonyls. Now for a double bond, remember we split the molecule and formed a carbonyl on each side as thus. So if you started with something like this, and whatever this is attached to, we would think about splitting this down the middle. Each of these attachments would still be the same, except now this carbon would just be double bonded to oxygen. Same on this side with whatever attachments being the same. For a triple bond, this is very similar, except we're making a carboxylic acid. Triple bonds don't have as many things attached to their carbons to begin with, and we're adding on further oxygens to those carbons. So similarly, we split down the middle. Our carbons are attached to a double bond oxygen, but they also get attached to an OH, making them a carboxylic acid. This is another functional group we brought up in the functional group chapter. So notice on this molecule, we have whatever R group attached to our carbon and another R group attached to this side. You split it in half. This carbon is double bound to an oxygen and it has an OH attached to it. And same with the other side. So very similar to our double bond reaction, except here we're generating always a carboxylic acid as our product when we do an ozonolysis. So let's do a sample. We're starting with 2-butyne. This is I'm drawing here. This pen is very bad. Okay, so 1, 2, 3, 4 carbons long. It's a butyne, and the double bond is on position 2 of the carbon. We're doing an ozonolysis, so we essentially break this in half. So we have a carbon here, It means there's a carbon attached to a CH3, right? There's a carbon on the end here. This gets a double bond oxygen on it and an OH. And on this side, it's actually a mirror image. So similarly, now these are the same molecule. They're just rotated, same molecule. So in this case, there'd only be one product technically because it's making the same molecule. It's a split that is even. And the answer here would be our B answer. So a CH3 bound to a carbon. This O2H like this is how you can write a carboxylic acid in shorthand. CO2H, that's the same as this. Normally you'll see it drawn out though. Now that we've talked about all of the reactions for alkynes, let's go into some retrosynthesis, again talking about these multiple reaction processes we've brought up and how you can go from the idea of a starting material and a final product and work your way between those. So remember, these carbon-carbon bonds can be formed on either end of an acetylene or an alkylation and can be used a lot to introduce carbon fragments into a chain. Remember, triple bonds are really good. Right now, we know because we have a reaction in which we can extend bonds, make a carbon-carbon bond to extend a chain. And then we can do things like sequential hydrogenation, either using the Lindlar catalyst or doing a full hydrogenation to give us reactions to either make an alkane or we can get to an alkene. So if we hydrogenate down to a double bond, we then have access to all of the reactions we talked about with double bonds. So here's an example to design a retrosynthesis. Design a synthesis in which you want to make 1,2-epoxybutane. That's this product. We want to make this product. And we're starting from ethyl bromide and acetylene. So we have 2 carbon sources that we're allowed to use. Ethyl bromide, that is a 2-carbon long chain, the bromine on it, and an acetylene, that is this carbon-carbon triple bond. So we only have access to these 2 things, and we want to make that epoxide. So normally with these retrosyntheses, you again want to work backwards. Start with the final product that you're interested in and think about how you can one by one get to that final product going backwards. So we know we've talked about epoxides and we know we can make an epoxide from a double bond. So for example, we could make this epoxide from this molecule with a double bond on it. We know how to do that reaction. Now, how do we get a double bond from a triple bond? We also know how to do that. We know how to go from a triple bond to a double bond. So we can make this double bond using a triple bond. Now, this triple bond is a little bit different than our starting material, but can we make an elongated triple bond using our starting material, that's 2 carbons long, and this other starting material, which is also 2 carbons long? We can make a 1, 2, 3, 4 carbon long chain with a triple bond. So yes, we can then make this from our starting materials. So let's think about then the process going forward on how to go from that triple bond to our final epoxide, now that we know each of the points to go through. We'll start with our acetylene and use a strong base to remove that proton to make an acetylide ion. This acetylide ion can then be extended using our ethyl bromide. This extends the chain by 2, so we get this product. Now we have our chain length. We went from a 2 carbon long chain to a 4 carbon long chain, butane, but we have a triple bond. To go from a triple bond to a double bond, we know that we can do a Lindlar catalyst, or we can deprotonate using this as well. But normally we're going to stick with the hydrogenation reactions we've talked about, specifically Lindlar reactions to go from a triple bond to a double bond. Lastly, and we talked about this last chapter, how do we do an epoxide formation? Here's our reactant for the epoxide formation from a double bond. Remember, this is this special molecule, which you have a oxygen-oxygen bond you don't see very often. Looks like this. So this is used for epoxide formation. This is again how you'd plan out a retrosynthesis, multi-step synthesis, starting with a few reactants and ending with a final desired product. Okay, and that is it for chapter 9 and for the rest of the lectures in Orgo 1. I wish you all well studying for your exams, and of course, come to me for any questions regarding this material.